In section 7.7 we're going to be looking at L'Hopital's rule, and we're going to go back into looking at the concept of limits, which you had in Calc 1. So first of all, L'Hopital. This is a picture of L'Hopital. He was born in France in 1661, and he died in France in 1704. So he had a pretty short lifespan, but in that lifespan he did accomplish quite a bit. He was a student of Johann Bernoulli. Bernoulli was a famous mathematician, and as it turns out ended up having quite a lot of influence in the field of statistics as well. Basically, he paid Bernoulli to give him private math lessons, and from these private math lessons he took notes, and from these notes he produced the first textbook on calculus, and that's kind of what he's famous for. He did not derive L'Hopital's rule. L'Hopital's rule is just named for him. And this is the formal definition of L'Hopital's rule that is in your textbook. So you can read through L'Hopital's rule, and then I'll try and go through and trying to explain it a little bit. So some shortcuts to L'Hopital's rule. First of all, we abbreviate a lot of times. Instead of writing out L'Hopital's, we often write L''H for L'Hopital's. So that is a shorthand notation for L'Hopital's. Up here in the definition, or the theorem for L'Hopital's, first of all it says that we have two differentiable functions, f and x. They're on an open interval, and in that open interval there is some constant a that we're interested in taking a limit of. Now this part here that says f of a and g of a equals 0, that's basically saying that down here, if I take the limit as x approaches a, I plug directly into that function and I get 0 over 0. And that's a very important point here. 0 over 0 is considered to be an indeterminate L'Hopital's form. There's other independent L'Hopital's form as well, but this is one of the more common ones. So if I get that 0 over 0, that indeterminate L'Hopital's form, this says that I can go ahead and instead of using one of my numerical or graphical approaches to finding a limit, I can just take the limit as x approaches a of the derivative of the numerator divided by the derivative of the denominator. This is not the quotient rule. And this is very important. This does not say the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. This simply says take the derivative of the numerator, the derivative of the denominator, take the limit as x approaches the same constant, and you will get the limit of the original functions, as long as, and this is something that's very, very important, the limit on the right exists. So for instance, when I take the limit here, I have to get a constant here. I have to get a solution. I cannot get 1 over 0. I cannot get infinity. That limit on the right must exist. L'Hopital's rule is used to evaluate limits of quotients that result in indeterminate forms. So an example of what this would look like, first of all it says a limit, so we're talking about a limit as x approaches some value, we'll say a, of a quotient. Now a quotient of course has a numerator and a denominator, and the result of this limit as x approaches a of this quotient is an indeterminate form. The indeterminate form so far that we have mentioned is 0 over 0. Now there are other indeterminate L'Hopital forms. Now these indeterminate forms are called indeterminate L'Hopitals because I can use L'Hopital's rules to solve them. 0 over 0 you'll recognize from previous sections as indeterminate, but now we know not only do we call it indeterminate, it's indeterminate L'Hopitals. Infinity over infinity is also an indeterminate L'Hopital, negative infinity over negative infinity, and any combination of positive and negative infinities written in a rational way. If I get one of these indeterminate L'Hopital forms, you can determine the limit by taking the limit as x approaches a of the derivative of the numerator divided by the derivative of the denominator. So after we get one of these indeterminate forms, I go ahead and I look at the limit as x approaches the same constant that we were working with in the original problem, and I directly take the derivative of the numerator, the derivative of the denominator. Now again, this is not the product or the quotient rule. This is L'Hopital's rule. So I take the derivative of the numerator, divide it by the derivative of the denominator. Now this has one very, very important caveat. This only works providing the limit as x approaches a of f prime of x over g prime of x exists. So for this answer right here, I cannot get does not exist. I cannot get infinity, therefore does not exist. I cannot get 1 over 0 undefined, does not exist. I have to get a value for this. Now L'Hopital's rule also works with one-sided limits. Now what we're going to do is work through a bunch of examples, and then we'll introduce another little bit more about L'Hopital's rule a little bit later on in the lecture. For our first example, let's go ahead and look at the limit as x approaches 2 of x squared minus 4 in the numerator over x squared minus 4x plus 4. Now we're going to work this problem a couple different ways. The first way that we want to look at this is actually by plugging in 2 and seeing what we get back out, and then going through and getting some algebraic approaches for a solution. So if we plug 2 directly in, I do get 0 over 0. This is indeterminate. Now before we got indeterminate, we would just say indeterminate, do more work, but now we know that this is a special indeterminate form called indeterminate L'Hopital's. Okay, so if I wanted to right now, I could apply L'Hopital's. L'Hopital's rule says then that I take the limit as x approaches 2 of the derivative of the numerator divided by the derivative of the denominator. So we go ahead and take the limit, and then I take the derivative of the numerator to get 2x. The derivative of the denominator is 2x minus 4. If you plug 2 directly in here, into the numerator I get 2 times 2 is 4. Into the denominator I get 4 over 0. And I have a problem. This is undefined. And because this is undefined, the limit does not exist. Now remember what the rule was up top. The limit as x approaches your constant of the derivative of the numerator divided by the derivative of the denominator, I call that kind of phase 2 of L'Hopital's. The limit has to exist, and because this limit does not exist, L'Hopital's cannot be used. I cannot draw any conclusions here. So no conclusions from L'Hopital's. That means I have to come up with some other different method. So let's go ahead and look at the same problem. Let's look at the limit as x approaches 2 of x squared minus 4 over x squared minus 4x plus 4 again. This equals 0 over 0, which is indeterminate. Indeterminate L'Hopital's, but I know it doesn't work. We'll just make a note of that. So what other approaches do we have? Well, we have an algebraic approach and we have a graphical approach as well. So let's go ahead and look at the graphical approach. As we look at the graphical approach here, and this is a graph I just popped in from Maple, we're looking at the limit as x approaches 2. So this is x equal 2. And this is actually not a vertical line. It's actually a vertical asymptote. But remember, a lot of times Maple doesn't catch those and just connects them as a straight line. So I'm interested in the limit as x approaches 2 of my function x squared minus 4 over x squared minus 4x plus 4. And I'm going to approach from the right in this direction. Over here I'm going to be looking at the same limit, but now instead of approaching from the right, I'm going to be approaching from the left. So I can see pretty clearly here that this limit is equal to a negative infinity, because you can see this just diving toward negative infinity here as we approach from the left. Over here, this is going up toward positive infinity, so the limit from the left does not equal the limit from the right. Therefore, the limit as x approaches 2 of my overall function does not exist. So now I've drawn a conclusion based on more of the graphical approach. So it does not exist. Again, because the limit from the left does not equal the limit from the right. That's why it does not exist. I cannot say it does not exist because of L'Hopital's. I have to say it does not exist because of the graph that I'm looking at, the graphical approach. I could also look at this algebraically and factor as well.